All right. Okay, homework. Let's get your workout. See if were there any questions, any issues with that calculator program we were doing. You need the program. Okay, here you need a half. Go ahead and get logged in. You need one too. Now, probably will not need the program on the quiz this week. I don't think we're going to. Oh, shoot. I don't think we're going to ask any questions on the quiz using the program. Just because there were some issues with the test mode. Although we may just do it, we may do it without the test mode. We'll see. But anyway, it doesn't really matter one way or the other. If you, again, the rule is if you have single-digit number of subdivisions to approximate, you write it out anyway. That'll probably be the focus for this. Okay, so let's see. I just need to set that to. So just James and. Okay, did it show up? You got to log in, I suppose. Yeah. Oh, my bad. I'm not plugged in. Down, give it to me.
Just look and see we would have this program.
Yeah, that's a great question. When it asks you for the M50s and stuff like that. I don't really know. I mean, I've always done that, and now I'm curious if, because it doesn't ever really say in there. Now, yeah, but like when it asked you on number, was it number 6, L20, R20, T20, M20? They really ask, I guess, some classes of students are maybe just lazy because one's a carny, so they would assume maybe they would assume you do it. I don't know. That seems like quite a few to do things. So maybe because the other, like the question where it asks about M100s and stuff like that, they're not really asking for the actual value, right?
They said look at back the example.
And they gave you some numbers. So yeah, maybe. So they made like the 20 subdivisions that may have been assuming you would go ahead and write those out. So I just, somewhere along the way, I've done it a lot of different ways and had different calculators, but usually had some sort of program to do. Did it work? Did it work? Did you get it? Okay, now what you need to do is this step right here. So if you would go, so if you've got it open, if you're on this screen right here, go to the dock button, and then number 6, I think it says refresh libraries. I think you may have to do that, and then it should work. We're going to try it here real quick. Just so we'll have Harish. I'm going to have Harish be a presenter here. Okay, so
Yeah, that's what happened. Like when I did
did you guys have that happen?
Well, he did, but he was typing something wrong. I came over and fixed it just like that.
Were you using the wrong E?
I think I used the right E. I did I'm pretty sure I did that. Yeah.
What?
And that's what happened.
Did it end up working?
I couldn't get it to work.
Which one? What number is that?
It was.
Is that number 6? That looks like number 6. James, Maya, to run this program, you go into the area program, you go to, page 1.2, so just control right arrow. So, yeah, go to current, okay, and then go to control right arrow. And I just hit it. All right, so, and then, so did you get into it?
Yes.
Okay, so go ahead and run it. Go ahead and run it here, Harish, and we'll have these guys do it too, so they can go through it one time. So RAM. So if you need to run the program, you just go onto the screen 1.2, type in RAM, parentheses, I'll hit OK. Let's go. Let's do like 6 decimal places. And then the function, let's put in e to the negative. Oops, that's LN. There we go. E. And then it puts in EXP here, but.
That's, okay, or the XP.
Oh, you got rid of the XP, that's the problem. Yeah, once, yeah, in this dialog box, that's what it does, because internally in the calculator, it's like sign, SIN, it's like absolute values, ABS, parentheses, it's like square root is SQRT, parentheses, right? If you've done any computer programming at all, they name that function, right? Just like this is really a function, and then there's a series of steps on what to go through. So the E is a function, right? The E to the X is a function, and so it's named EXP inside the thing, and so that's what it's, okay? So when you type in this dialog box, it writes it as a function. So anyway, put negative X squared. Okay, so this would be number 6. Number 6, where we had to do our L20, R20, and those things, okay? So hit OK. And then, what was it? It was from 1 to 3. So left bound 1, right bound 3. We want to do 20 subintervals, okay? So hit OK. There you go. Okay? So there's your L20 approximation, your R20, your T20, your M20. Now, Simpsons is not right, though. Simpsons, this would be an M20 or an S20, and they wanted an S40, right? So you got a choice. You could take 2 M20s and a T20, add them up, divide by 3, right? Use that shortcut. Or you could rerun the program. You could rerun the program and type in a 40 for the number of subintervals. Okay? But it's pretty much accurate. I think you're going to get the same thing. I mean, the way this one looks. I mean, here's the exact answer here. Simpsons is already accurate out to 6 decimals. Okay? Okay.
Mr. Clark?
Yes.
So can we get to the actual code on our calculator?
Yes, absolutely. So, Harish, hit control right arrow. It's out on page 1.9 is where it is. Now, just be careful not to edit it in a manner that would. Here it is right here, yeah. So here's the program. This is the comment, the little C with the circle. That's a comment line, so it just nothing's happening. Oops, go back. Yeah, we could run through it here real quick. I'd just show you what's happening. This is just some mode things. There's some instructions on what the different modes are. So that the 4 and the 2 means something there. It's been so long since I did this, I don't even remember. Well, I edited this program. Yeah, I borrowed the code. It was for another calculator for our old TA84s, and then I adapted it here for the T8 for the Inspire. But anyway, so when you ask how many decimal places, it puts that in, and then this is another mode. This is a mode setting for that, and this is where f of x. That's why that f1 of x shows up. And so you're just storing these requests, or just those dialog boxes, just storing values into variables, A and B, number of subintervals in. Keep going down here. This is just for an error message. Mod N2, mod is just a division, and if you have a remainder. Okay, so if mod N2 equals 1, so what that means is if you take the number of subdivisions, divide by 2, and get a remainder of 1, that means it's odd, right? If you take 9, divide by 2, you get 4, remainder of 1. So mod is just the remainder. So if that equals 1, then the program's saying, okay, you put in an odd number of subintervals, you can't do it. So it's just a check for an error message. If it's even, then the mod will be 0. So that's what that is. And then this is just a sigma, this is just to add them up, okay? So this is like your left, I just called that LRAM. But H is defined over here, so I got a vertical bar width, H equals B minus A over N, so H is just, I just used H for the width. And then if I starts at a 1, so this would be A plus 0H, and then when I is at 2, this would be A plus 1H, and then A plus 3H, and so just add on a width, just keep adding on a width. And I was going to say, I didn't go 0 to N minus 1. I guess that's because I did I minus 1 in there. So I could have done 0 to N minus 1 for the L, RAM, RM. Anyway, go down through there. So that's just going to use a sigma to add them up. And there's trapezoid, so forth. And then the actual integral, and then just do it. So it's, you know, it's nothing too fancy, but it uses that sigma and uses that, well, you know, same thing we did when we wrote those sigmas early on. So, all right. So anyway, be able to use that. That's pretty simple. Anything else in the homework, any of the calculations, the over and under approximating, all that stuff, that's going to be a big part of the quiz on Friday, where we have to know, you know, obviously if it's increasing, then that determines whether left and rights are over and under approximations. If it's concave up or down, that tells you if trapezoids or midpoints are over under approximations. We don't really have anything for Simpsons, whether Simpsons is an over under approximation. We're going to talk a little more about Simpsons here today. These would be good to know, I mean, as far as how you write them out, but I don't care. Remember, single digits, you're not going to have to do more than 9 left rectangles and 9 trapezoids. If you want to write them out as rectangles, you want to write them out as trapezoids, that's fine. Or you want to write them out using these, that's fine too. And then, of course, you got those formulas that you can use. And then we were talking about the max error kind of idea yesterday. Okay, so any of the homework ones you want to talk about at all? Because these could be ones that would be on the quiz, so I don't want to shortchange if you have some questions. Which ones? 20?
Yeah.
Okay. So in 20 it says, let I be the integral from -2 to 5, where f is increasing over this interval. Furthermore, suppose that L10 and R10 are those values right there. So you can tell that L is under and R is over, and that makes sense because it says it's increasing, okay? Explain why. So I minus L10, why is that less than or equal to, did I get that right? R10 minus L10. So this goes a little bit to yesterday when I was talking about, okay, here we know L10 is here, and that was 9.4132. And this is R10 over here, 9.5768. Okay, I is in here somewhere. We don't really know where. Okay, so remember, what does this mean? When you see this, what does that mean to you? What do you think of when you see this left side in words? Amount of error that L10 commits, right? L10, something wrong, commits, right? L10 has that much error. That's what the left side is. So if the amount of error is less than or equal to this is like saying this is the max error. So this side is like saying the max error, because you have this less than or equal to. Okay, since I has to be in here somewhere, because we know if L is under, R is over, we know I has to be in here somewhere. The worst case scenario is if I, the actual area, this is the actual, if the actual area was way over here, how far off, what's the most that L10 could be off? Well, it'd be the distance from here to here. Does that make sense? So, and the most, you know, maybe I is right up against there. So the farthest I could be off from L10 is the difference between R10 and L10. So that would be just kind of your explanation. Maybe a little picture, maybe some words. Okay? Evaluate T10. Okay? So T10 is simply going to be 9.5768 plus 9.4132 divided by 2, right? Average the left and the right. T10 is an average of L10 and R10. So you calculate that, whatever that comes out to be. And then explain why I minus, and then they give a hint here, because we just, they give you that hint. So then the next one says, okay, here's L10, here's R10. We know that T10 is where? Right smack dab in the middle. This was that thing we talked just a little bit yesterday. So T10, whatever, I don't know what you came up with that, but whatever, doesn't matter. So you average them, so we know T10 is right here. So now what is the most that it's off? Well, that would be if I was like way over here. Well, it's just going to be half of. So if you do R10 minus L10 and divide by 2, which they say that's 0.0818, then that's this distance right here, 0.0818. So if I is way over here, which it probably isn't, but if it was, then T10, the most it would be off would be that distance right there. And that's the 0.0818. Okay, so again, same thing. The most it can be off. Now we're going to fine tune this today. That's the whole goal today, is to really talk about this idea of error, max error, and so forth. Okay? But that's the idea. That's the idea. That we can trap it, that we know a left is under, a right is over, and that tells us about how much error there is. Okay, what else? What else? Okay. You got that whole section of must be true, might be true, can't be true, right? Okay. So again, if you're questioning those, check them. Check them over here and make sure you get those right. Okay. And we'll have a chance to rehash this a lot on Thursday, all this stuff, because we got some stuff to do today and new stuff to do tomorrow, but then Thursday we can kind of revisit this. Okay? All right. Let's move on then, because this is going to take just a little bit of time to get through here today, what we want to do here. So what we're going to do first is we're going to talk about left and right rectangles and what causes them to be off. Now, how much of this you actually write down is up to you, right? You're not going to have to redo this, but I really think it's some value for you to see this. Where these kind of strange formulas we're going to be using come from. The most important thing for you, though, on the quiz is to be able to use these formulas that we come up with at the end. So if you want to just follow along watching it, I'm fine with that. Okay? So what we're trying to do is figure out what's the most, a left or a right. Now, we're just going to do a left here, and the right works the same way. What causes a left rectangle to not be an exact approximation? If the function is what? Well, let me word it this way. What kind of a function would a left rectangle be perfect for? Oh, straight? There you go. Horizontal line, right? Horizontal line. All lines are straight. Horizontal line, right? Horizontal line. Okay? Right? Miss Stockton, is this a straight line? Yeah. Well, you gotta be a little careful with my drawing. That is a straight line right there, right? That is not. Okay. Horizontal line. Horizontal line. Horizontal line would be perfect, but not many functions are horizontal lines, right? And so diagonal line is going to be off, right? There's going to be some error. And when does that error get worse? When the line is what? Steeper. The steeper the line gets, the worse it is. So what causes there to be error? The steepness. If only we had a way to measure steepness. Slope. The derivative, first derivative, is going to be the error. So we said we want to do a worst case scenario. So a worst case scenario, we're going to look at a function. Now we're only going to do it in one subinterval. Notice this is just one subinterval. X of I minus 1 to X of I. So we're just going to look in one subinterval. We're going to look at the function, and we're going to call K1 the max slope. Okay? K1 is going to be called the max slope. In other words, we're going to look at that function, and we're going to find where its derivative is a max, right? That would be the max slope. okay, which we'll get to here in a little bit how we do that. But we're going to find the max slope, and then you know what we're going to do? We're going to pretend that the function has that slope the whole time. So maybe right here it was the steepest, or maybe right here it got the steepest, whatever. But somewhere in there, we're going to take that slope, and we're going to pretend that it had that slope the whole time. Wouldn't that be the worst case scenario, right? So we're going to pretend it had that slope, and we're going to pretend the function does this instead of does, holy cow. We're going to pretend that that function does that the whole time. So here's the actual error. The gray is the actual error, but this is going to be our max error right here. This triangle, that's the most we could be off, right? Because the graph can't be any steeper than that because we took the max of our derivative, okay? All right, so now the question is, what is that blue area right there? That's going to be our max error right there, okay? That's going to be our max error. Now, how do we write that? Well, we just said that a minute ago. The way we write max error, what? Error. That's an O. All right, so that's what's going to go right here, is our max error right there, okay? All right, so how do we count? So that's what this triangle would be. So how do we do the area of that triangle? Well, it would be 1/2. It would be the base. What's the base? Well, I said this was one width, right? So this is going to be delta x, right? Well, what's delta x in these problems? Yeah, we could do that, but better even still. What was our formula with our width of rectangles? B minus A over n. B minus A over n. So yes, we could call it xi minus xi minus 1 or whatever, but we're going to assume they're equal width rectangles. Remember, this is just one rectangle we're doing, one subinterval, and then we'll multiply it by how many rectangles we have. Okay, so B minus A over n is going to be this. And then what's our height? Well, let me see. K1 is my slope, and slope is rise over run, right? K1 is going to be rise over run. K1 is my slope. All right, well, what's another name for the run? Oh, we just said it. Delta x, right? That's delta x. And the rise is what we're looking for, right? The rise is what I want to know. I want to know the height of this rectangle. Well, that's the rise. So it's rise over run. So my rise is going to be delta x times K1. Make sense? So the height of my triangle, so I got 1/2, base of my triangle is this, and the height of my triangle is going to be delta x, which is also B minus A over n, right? Right? That's what delta x is. My run times K1. Okay? All right? Let's rearrange this a little bit. Okay, let's go to the next screen. So we're going to have B minus A over n squared times 1/2 times K1. Okay, I can do that a little better. I'm going to take the top, and I'm going to put K1 there, and I'm going to put B minus A squared there, and then the bottom will be 2n squared. Okay, there you go. That is my max amount of error. That's this area, and we're assuming, forget that blue squiggly function, we're going to pretend the function does this. Here's our left rectangle approximation, so this is the max error right there. And that area, that error, is that triangle. It's right there. Okay, now that's only for one subdivision. How many subdivisions do I have? I have n subdivisions. N is the number of subdivisions. So I'm going to multiply that by n. That's going to cancel that. And so there is going to be my formula, and I'll write it out a little better here. Well, let's just do it right now. So this is I minus L sub n. This is what your book, I think, calls a theorem 1. For some reason, they just call this theorem 1. Okay? Somewhere in there, no, they call that theorem 3. So in your homework, it says, compute a theorem 3 error bound. Well, this is the formula they're talking about. Now, the most important part of this is right there, that this is the max of f prime. And it's actually going to be the absolute value of f prime, because what makes there be error? Slope. Well, if the slope is positive, that means the left rectangle will be under. And if the slope's negative, the rectangle will be over. We don't really care if it's an over or under approximation. We just care about how much error there is, right? So we're gonna so if you had an F graph And for a while it went up as steep as 2. And then a little later it went down as steep as -3. Which one of those do you suppose you'd use for K1? Which one would cause the most error? A slope of 2 or a slope of -3? The -3, right? We don't care. So we're going to do the absolute value of f prime. So the number we would use in that case for K1 would be 3. If you had a slope of 2 and you had a slope of -3, the one we want, the max, would be the 3, right? We don't care about the negative, right? We care about the steepness, okay? So K1 is the max of f prime. So that you should write down, right? That you should have. Now, I'm not going to make you memorize these. These will be on the quiz, okay? These formulas. But you're going to have to know what K1 is. You're going to have to know that K1 is the max of f prime, and you're going to have to know how to find it. Okay, so let's use it in a problem. And it's the same formula for R. Same formula for right rectangle. Okay, so let's look at a problem where we use that. So let's do the integral from 0 to 1 of sine of x squared dx. And let's find, your book will call it a theorem 3 error bound for, let's do 10 left rectangles. Okay? So, Harish, first of all, now remember, we don't know the exact value unless we cheat and type in our calculator. But we don't know the exact value of this because there's no antiderivative for sine of x squared, right? So Harish and everybody else can do it too. We're going to get on here and let's go ahead and do an L10. So let's run the program again. Yeah, let's go 6. Let's go sine of x squared. That's fine.
Okay,
just hit enter. You can just hit enter again. You don't have to type it every time because it's going to do the last thing you did. You know what I mean? It'll do the last thing you did, so you can just hit enter. Okay, 6 decimal place, sine of x squared. Zero to 1, 10 subdivisions. Okay, so there's our left, 0.269097. Is that right? Did I do that right? 269097. Okay, and the actual is 310268. Okay, all right. So anyway, so we're obviously off, and again, pretend we didn't even know this. Okay, just pretend for right now we didn't even know it. So let's see what is the most this could be off. What's the most it could be off? Well, this is where we're going to use this formula. Here's how we're going to do it. I'm going to put a box right there. That's where K1 is going to go. And then I got b minus a squared, so that'd be 1 minus 0 squared over, what was it, 2n? Was it 2n? So 2 times, what goes in for n? 10. See how you're going to know all that? You're going to know the a and the b. You're going to know the n, right? And what you're not going to know is a K1. So on the quiz, here's what I'll be looking for. I'll be looking for that box right there. I'm going to be looking for what number you stick in for K1. So here's how we're going to do it. Remember, K1 is the max of f prime absolute value. So here's how you're going to do it. So you're going to go to your calculator. So obviously the calculator will be important on the quiz. Okay, let's go to your calculator. Get out of the program there. Hit OK. Okay, let's go to a graph screen. So go to your scratch pad. Okay. You know what I would do? Here's what I would do. I'm sorry. Let's go back to your calculator screen. Hit that again. Okay. Let's do the derivative of sine of x squared. What the heck? We got our calculators. We all know we can do it, but kick out a 2x, whatever. But let's just do the derivative of sine of x squared, because it might be a messier function, so let the calculator do it for you. Hit enter. Okay, now I would go up and copy that. I would go up and copy that derivative. Okay, so I would go up there. No, I mean just arrow back up. Yeah, arrow back up there. I hit Control C for copy. Now you could type it. It's not that big a deal, but sometimes it gets kind of messy, so just Control C. Okay, now let's go to your graph screen. Okay, and let's get rid of whatever that is you got in there. Okay, now what I would suggest, let's do it both ways. So let's go ahead and type in, just go ahead and paste it in. Now hit enter. Okay, now we only want to look at this. So what I'm doing is I'm graphing the derivative, right? And now I can make you go through a whole thing. We're trying to do the max of this. We can do the derivative of it, set equals 0. Okay, that's too much work for what we need for this. So we want to find the max of that because this is the slope. But we only need to look at it from where to where? 0 to 1. So we're going to do a zoom fit. So we're going to go menu, window, window settings. We're going to put in our 0 and 1 as our X-min and max. Okay, hit OK. Don't put anything in for the Y. We're going to zoom fit that. So we'll go 0 to 1, and now under menu, it's pretty good right now. So, but go ahead, go to zoom fit, which is A. Okay. All right. Now notice it's always positive here, so we're fine. But here's where you have to be careful. So let's say that graph went up to a height of 2, and then went down to a height of -3, right? What number do you want to use? You'd want to use 3. Now, the other thing you could do before he pasted that in there in F1, he could have done absolute value, right? He could have done absolute value and then pasted it in and done the absolute value of it. That would have flipped all the negatives up to positive, right? You could do that. So if you want to do that, then all you have to do is pick out the highest one. Okay? Now, I do want you to understand that because I might give you one like this. I might give you a problem where I just give you the graph of F prime and I do exactly what we were just saying. And this is a height of 2, and this is down here, I think your homework does this, of -3, and I ask you, what's K1? You know, and I'm going to want you to say 3, right? K1, the K1 value to use is 3, right? Because if this is F prime, the max of the absolute value of F prime would be 3, because this part would flip up, right? So if you use the bars, that would just flip this up, and boom, there'd be your K1 right there. Okay? So just so you understand that. Now, problem is the K1s aren't going to be that nice and rounded. So let's arrow up to there. Nice thing about your calculator is you do have a max feature. But if we go to trace, go to menu, trace, graph trace, right arrow. And remember, when you get up there close, it'll tell you where the max is, which is nice. If you're not seeing this many decimal places, I think you want to go to your settings and change it to float, if you remember. I think Horatius is set, but sometimes when we run programs or do different things, sometimes our calculators get reset. Keep going until you get to the max, and then there you go. Oops, went too far. There you go. Okay, now go to menu and settings, and notice his is set on float. So if yours is like float 3, if you're only getting a couple decimal places, you might want to fix that right now. So it just says float. Okay, so go ahead and escape out of there. All right, so that's what we want. So now the question is, and I'm going to be real picky about this. What are you going to use for your K1 value for this problem? Remember, we're wanting it to be a worst case scenario. We're wanting K1 to be the max slope. So if you said it's 1.2, would you be right? 1.2 is not the max, it's bigger than that. 1.28, would that be right? 1.283, would that be right? No. What do you need to do? You need to round up, right? So I will have on the quiz, I'll have this number written out to 7 or 8 or 9 decimal places. I don't care how far out you go. Now you need to pick a number that would be reasonable. So for example, I wouldn't like you to use 1.3 here. To me, you've rounded that up too far. Okay? Now, if the number was 197.28 something, well, taking 197.28 and going to 197.3 is not much difference, right? But 1.28 to 1.3 is a little different, right? You see what I mean? Relative. I would rather you go, and maybe you want to always go 3 decimal places like we usually do. I don't care. I don't think you would have to if the number was bigger. But when it's a number like this, Okay, so to me, 1.284 wouldn't be a bad one to use. 1.29 would be fine, but you should always round up because we want it to be a worst case scenario. I want K1 to be a number that the slope will never be more than, right? When we talk about a max, so let's go 1.29 here. Let's go 1.29, okay? So whatever decimal you want to end on, round up is basically the bottom line, okay? You want to go 1.284, I'm okay with that. All right, so back to our work. So we're going to use 1.29. So that's the number I'm really looking for in your work. That is the max slope. That's the steepest this graph sine x squared will ever be. Now remember, we graphed f prime. So it's important to understand we didn't graph that, we graphed f prime. Okay? All right, now we just do the math. So now you just get your calculator out, you do that, which is basically 1.29 divided by 20. And what do you get? 0.0645. Okay, so what does that mean? That means that's the most that this is off. That's the most that this is off. Okay, now we could write a couple different things. They may say write an error bound. Well, what you can do then is you can just take L10 and you could, you could take your L10 number and you can just add this on and subtract it off, right? So you could do 0.269097 plus 0.0645. And over here, 0.269097 minus 0.0645. We know the exact answer has to be somewhere in between there. Now, it turns out that this is increasing during 0 to 1, so we actually know the left is under, so we can actually, add that on and whatever. Say it's got to be somewhere in between 0.26 and whatever. Now, how much is it actually off? Well, since we know that the exact answer we already looked at, if we subtract these, do that for me, Harish. Let's subtract our actual answer minus our approximation here. So it's actually off by about 0.04, okay? So this does, remember, it's important to understand, and I may ask you about this to explain this. This doesn't tell you how far off it is. It tells you what? The most it could be off. The most. So we're getting close now to that question of how does the calculator know that it's accurate to within 10 decimal places? Well, this is how. This is how. It doesn't actually know it's accurate to 10 decimal places. It knows it's at least accurate to 10 decimal places. It's probably even more accurate. So this number is just saying, hey, we are within 0.06 of the right answer. Okay, it turns out we were within about 0.04. But that's because we chose the worst case scenario. So chances are, whatever number we get here, chances are the actual answer is closer than that. Okay, the other thing you can see is however many zeros you have here means you're within that decimal place. Okay, so if you have a 0.6, so we could say, okay, rounded, this decimal place, we're at least accurate to this. This would round to 0.3, right? Because of that 0, we know we'd be within a rounded in that decimal place of being accurate. Okay, so let's go ahead and let's talk about trapezoids and midpoints. Okay, what causes a trapezoid to be off? Concavity. Okay, what would make this be off? Back up. What kind of a function would a trapezoid fit perfectly? Any kind of line. Any kind of line. A diagonal line, a trapezoid is going to fit perfect, right? But you get a quadratic, you get something with curviness, okay, with a curve to it, that's going to be off. What's going to make it be off more? I don't know that we've ever talked about this. We may have at one point, but the bigger that f prime is, the steeper the line is. We all know that is slope. Did we talk about this, that if f double prime is 2, how does that compare to f double prime being 5 or f double prime being 8? It's more curvy. It's more concave. There's a more curvature. So the more curvature there is to the graph, the more error there's going to be. So we're going to do exactly the same thing. We're going to call it K2. And K2 is going to be the max of the second derivative. That's going to tell us the curviness of the graph, and that's going to determine how much error there is on a trapezoid or a midpoint. Because remember, a midpoint is a trapezoid too when you pivot it. Okay, so here's what we're going to do. Again, you don't have to write this down. But again, K2 is going to be our max of F double prime. And again, we don't care if it's negative or positive. That just tells us if it's concave down or concave up. Okay, K2 is going to be the max of F double prime. So the 2 helps you remember double prime. K1 is F prime. Okay, all right. So let's assume then that we have a function. So worst case scenario. So what I did on the last problem is I assumed I had a function that had a K1 slope the whole time. Well, that's a lie. Okay, so I had a function that had the same slope the whole time. That's a lie. Okay, this time I want to assume a function that has a K2 second derivative the whole time, right? Worst case scenario. K2 is our max curviness. Let's make up a function that has that curviness the whole time. Okay, so it was easy with a line, and then we just had a triangle, so that was easy to do. Okay, well, here's what a function would look like that has a K2 second derivative the whole time. So we want to know what f is, the original function. So let's do the antiderivative of that. That'd be K2x. So that'd be f prime. Let's do the antiderivative again. For plus c is not going to matter. Let's do the antiderivative again. Raise that up to a 2, divide by 2. This would be a function, this parabola would be a function that would have a K2 second derivative all the time. Okay, now, a little trickier here, because since this just made a line, our max amount of error was just a triangle. Okay, so we just did that area of a triangle, so that made that easy. We're going to have to get a little fancier here. So what I want to know is how much error there is between my exact answer and my approximation. Okay, so what I need to do is I need to find how much area is under is this one, and I need to find how much area is this one, and then I need to subtract it. Okay, so I need a way to find the exact area under this. Now remember, we only did one subdivision earlier, so we're just going to do one subdivision. Now I'm going to do like I did in my program. I'm going to call one subdivision H. I'm going to let H be my width, and we'll call it B minus A over N here in a minute. But for right now, I'm going to call it H. So I'm going to do the area under one subdivision. I'm just going to go from 0 to H. Okay? So that's going to be the area of one subdivision of this function right here. Okay? So that's going to be my exact area under this made-up function that assumes I have the worst concavity, the most curviness the whole time. Okay? Then I'm going to do a trapezoid under that same function. Okay, well, a trapezoid, I'm going to do one trapezoid. Well, a trapezoid is going to be that. It's going to be f of 0 plus f of h, right? Those are my two endpoints, 0 and h. And then what's the width? What's the width? H, right? H is my width. Okay, so I need to calculate these two things. So this is going to be the actual area under this curvy function. And then down below is going to be one trapezoid below that curvy function. Now I'm going to subtract those, and that'll be how much I'm on, right? I'm going to subtract those two, and that'll be how much I'm on. Okay, so this will be easy. The K2 is just a constant. So raise that up to a 3, divide by 3. So that'd be 1/6 K2x cubed from 0 to h. So I'll plug in an h. That's going to be 1/6 K2h cubed. And then minus 0. Okay, so that's easy. Okay, and then this is going to be 1/2 f of 0, so I put a 0 into there, that's going to be 0, plus, then I plug an h into there, that's going to be 1/2 K2h squared, and then times h. Okay, so what do I got? So my I here is 1/6 K2h cubed, and my t is what? What would that be? 1/4 K2 H cubed. Oh, nice. They're going to be like terms, right? And so what is this? 2/12 minus 3/12. That'd be negative, but do I care about the negative? Right? Usually we do bars around that, right? It's how much I'm off. Okay, so it's negative. So I mean, it maybe it was a over approximation, but whatever. So that's going to be 1/12 K2 H cubed, right? Okay, I'm getting somewhere. So then this, so let's write that. So that's going to be 1/12 K2 H cubed. Now H, remember, was what? B minus A over N, correct? So the H was one width, that was the width. Okay, so now I can rewrite this as a fraction a little nicer. I can put the K2 on top, I can put the B minus A cubed on top. The bottom's going to have a, oh, whoops, that's a 12. That's a 12. And now I have a 12N cubed, correct? And then, but that's the error, so that's the amount of error, that's the amount of error in this worst case scenario, but that's only for one subdivision, so I have to multiply that by N. So that's going to cancel there. So I've got it. So here we go. I've just got my formula. So I minus T sub N is going to be less than or equal to K2 parentheses B minus A cubed over 12N squared. Okay, there you go. That's a formula that we will do. And remember, K2 is the max of F double prime absolute value. That's what K2 is. And we'll find it exactly the same way we did K1. Okay, and that gives us the max curviness. Okay, and then likewise, I'm not going to go through it, but we can do the same sort of thing. But remember, a midpoint was actually, we said, roughly twice the accuracy. So its formula is actually very similar, but we're going to divide that amount of error in half by having a 24 down there. So the amount of error, the max error for a midpoint is actually half what it would be for a trapezoid. Okay? And it would be a similar line of reasoning that we would go through there. Okay? It's just a little messier on the algebra. So, again, don't worry too much about how we got to that, other than hopefully understanding why K1 and K2 work the way they do. That K1 and K2, we make up a function that would be the worst case scenario, and then we assume it has that the whole time, which it clearly will not. And then, therefore, we know what's going on. So we got two more types of problems to do. Let's do one. Let's do one for this sine of x squared again. Okay, so we got, all right, so basically there's our formulas right there, right? So there's, and again, these will be given to you, but you're going to have to know what K1 stands for and what K2 stands for. I won't, this part I probably will not write down on the quiz, okay, but the other things I will have there. Okay, all right, so let's say we're going to take R or T, let's do a T10, okay, for that same one. So that same integral, 0 to 1, sine of x squared dx. Okay, we know the right answer was what? 0.310268. We know that's the right answer. What was our T10? You still have that up on your calculator? So T10 is 0.311171. Okay, so we're not off too far. Let's see what the formula tells us we're off. So let's go I minus T10, right, would be less than or equal to, and so here's going to be K2 right here. K2 is going to go in there. B minus A cubed over 12 times 10 squared, right? That's our formula. Right, B minus A cubed over 12N squared when we're doing the trapezoid. Now our job is to find K2. That's the part I'm really interested in these problems. That's probably the hardest part you know, it's not hard, but it's the most work of doing this. Just follow the formula. So let's go back to your graph screen and maybe back to your calculator screen, and go back to your calculator screen. And so we need to get the second derivative, right? We need to get the second derivative. Now there's a quick way to get second derivative if you just go up to your derivative area there. Okay, well, okay. Well, yeah, that's fine. Just do the derivative of the derivative, that's fine. But you know there's the one where you can put in the 2's. Go here, Therese. I want to show you this. Looks like you go into the menu, which is fine. But you can do second derivative right here. Right? You can do second derivative right there. Hit enter, yeah, and then you just put your x, and then you put sine x squared in there. But yeah, once you've done the first derivative, you can just do the derivative again. Right? Same thing. Okay? All right, so I would arrow up, copy and paste that. Okay, and we want to graph that. Let's do the absolute value this time. Let's do the absolute value this time. So we go into your graph screen, hit the tab, and there you go, arrow up, delete that out of there. And now do the absolute value. So if you go, it's in here again, and grab the absolute value right there. And then paste. And now Control V, and you can paste that in. Okay, so you can see how it flipped it up. Then you don't have to worry about, you know, the positive and negative part of it. So it's totally up to you. Let's do a zoom fit on that. We still have our window set from 0 to 1, so we can do a zoom fit. Okay, now it's a little tough to tell which one of those is the high point. Is it on that far right edge? You can always trace. It looks like it's there, so we can trace right at 1. Good thing to do might be, it looks like it might be at the far edge, so you might trace to 1, okay, and you get that point there. And then you might trace to 0, because it looks like it was kind of high back there at 0. So you might put in a 0. Oh, okay, see, that's a 2. So it looks like the high point is definitely right at 1, okay. So what number do you want to use then? So what do we want to use for our K2? 2.286, I love it. 2.29, I think would be okay. You know, 2.3 maybe, but I don't know. Let's go a few places. 2.286 would be fine. Always round up that last one. Always, we're not using the normal rules of rounding. So what do we say, 2.286? Okay, always bump up that last digit. That way you know you're picking a number that is the worst case scenario. Okay? And now we just want to multiply this out. Now make sure you get your parentheses right and everything else you do on your calculator here. So 2.286. Now, yeah, 2.286. And then, of course, that other part is just 1 cubed. So there's no, you know, do you write it? You know, who knows? Harish does. Okay, 12 times 10 squared or 100, right? Make sure you get the fraction. Okay, good. 0.001905. So this is what your book's going to call a Theorem 3 error bound, right? Find a Theorem 3 error bound, and then that's what you're finding right there. And that's the number I'll look for, right, on the quiz. Well, I'll be looking at this box to see what, so you're going to have to show your work. So when I give you these formulas, I want to see this written out, right? I want to see what number you used right there, okay? And then here it is. And so this tells us we're within a couple of decimal places, especially when there's only a 1 right there. You know you're not going to have much rounding error there. And sure enough, 0.31, 0.31. So that's how we can tell. Okay, so the most interesting to me problem of all then becomes this one. How many rectangles, or how many, I'm sorry, we're going to do trapezoids. How many subdivisions needed? And this is what your calculator does internally. There's a algorithm that goes through. How many subdivisions needed to get the error within 0.0005? Okay? So this is the last type of problem we want to do. So what you do is you set this up and you say, okay, I want my max error to be within, now which formula are we using now? K1 or the K2? K2, because it's a trapezoid. So that's B minus A cubed. Oops. Same problem. We're doing the same problem here. So this is going to be K2. It's going to be 1 minus 0. And then it's going to be 12n squared. We don't know n this time. And we want it to be within 0.0005. Okay? Well, what did we just use for K2? 2.286. So now what we do is we just have to solve this equation here for n. And you can do this right on your calculator. Now we can multiply that over and divide, whatever, but why not just let the calculator solve this? So what we want to do, but let's say that we started this from scratch, right? How many subdivisions needed to get this within 3 decimal place accuracy? That'd be 0.0005. 3 decimal place accuracy, how many digits needed, or how many subdivisions do we need, or how many trapezoids do we need? You would go through and still have to find your K2, which we already did, okay? But now we're trying to find the n instead of this number over here. So now we just go to our calculator screen, and Harish already has it for us. No. Solve, so we're going to go to solve. Okay, and so then we put our fraction. So 2.286 times 1, right, over 12n squared less than or equal to, which is in here, less than or equal to 0.0005, and then comma, solving for n, hit enter. Okay, so we would need, now we just did 10 and we were within 2-digit accuracy. So what would you put for your answer if the question was how many subdivisions are needed?
19.
You can't do 19.5 subdivisions. 20. You'd say 20 subdivisions, so greater than. So if this would have said, we ignore the negative, and if this would have said 19.1, you'd still say 20, right? You need 20 subdivisions to get this degree of accuracy, okay? To get this degree of accuracy. All right. So what if we wanted way more accuracy? So arrow up there and grab this again. What if we wanted to get 10 decimal places of accuracy? Okay? So we want that to be 10 to the negative 11. So change that 4. Yeah, change that. No. Well, okay. Just delete. Point, and now do 10 zeros, and then a 5. You could have just changed that to 5,
yeah.
Negative 11, but that's fine. And put a 5 there. Okay? And we could put a 1 in there too. It doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right. Now, how many trapezoids would be needed to get that amount of accuracy? So enter. So the calculator's running some sort of routine to figure out how many subdivisions are needed to get this amount of accuracy, and then it's going to do the approximation with that many. So it would take 61,726, probably way less than that, right? If we did 61,000 trapezoids, we'd probably get 13 digits of accuracy, right? Because this is worst case scenario. But this would guarantee us that we would be accurate out to 10 decimal places. Make sense? Okay. Now, here's what's kind of interesting about this is, we'll save that for later. Okay. I did this one year. I'm gonna give you some work there. Simpsons. Any guess in how many subdivisions Simpsons would need on this problem to get the same amount of accuracy? A third, 20,000. Well, midpoint actually takes about 42,000 to guarantee. 237 subdivisions, or 238 or something like that. 238 subdivisions would give Simpsons would give you out to that amount of accuracy. So you can see how the calculator can do the Simpsons much faster because it needs so much fewer subdivisions. So if you ask that program, well, you guys can try it. I don't know, you might like it for calculator. that area program and ask it to do, 10,000 subdivisions or 61,000 subdivisions, it may run for a while. It may run for a while. I'm not sure it'll run that long. It should be able to handle it, but that's up to you. Okay, here he goes.
So, Mr. Clark,
Yes.
so why is Simpsons so much more accurate?
So Simpsons, okay, so you know how we said left and right will fit a horizontal line perfectly, okay? And a trapezoid and a midpoint will fit a linear function perfectly. Well, Simpsons is actually designed to fit a quadratic. Simpsons actually fits a quadratic equation perfectly. However, it turns out you get 1 extra degree for free. Simpsons actually fits a cubic even perfectly. Okay? Now, so what happens then is, so that means there's no error at all for a cubic. Now, one of the things you study in Calc 2 is called polynomial approximation. That is where you take like sine curves and e to the x curves and things like that. And if you look at, you know how we've talked about, if you zoom in on a graph that curves, it'll look straight. If you zoom in on a little piece of the graph, even if it curves, it looks straight. Well, it turns out if you take a piece of a sine graph or a piece of a e to the x graph or ln x graph, you could fit a polynomial to it pretty accurately, right? And so what that means is the vast majority of, still going, so different sine graphs, different types of equations, we can fit pretty accurately with cubics and fourth degrees and stuff like that. So, and that's kind of what Simpsons does. So since it fits those so good, now, I'm not going to have a good answer for you why it fits it quite so good, but it has to do with, the whole midpoint trapezoid combination thing, weighted average thing. That you just don't get much error. You just don't get much error when things are curving because it's like having a quadratic or a cubic fit to it, which it can fit pretty good to most things that curve. So that's partly why. The formula for Simpson actually uses the fourth derivative because of that thing, what we just said. Since it fits a cubic perfectly, we go to the fourth derivative, okay, so Harish probably won't get to do his homework, but the rest of you can start on 6.2, that next line, okay, the 6.2 line. There is a little more discussion, John, to answer your question. I haven't looked at it for a while. At the end of this chapter, there's this interlude, it's called. There's 2 pages where it talks more about Simpsons, if you're interested. Start.